Alrighty, hi everyone. I hope you are having a great week, and tomorrow is Friday, so yay. For this review session today, if you have any questions, feel free to pop them into the chat, and I'll get to as many of them as I can. I did have one student already send me a couple questions, so I'm just going to start there. They're not necessarily related to the practice exam or the homework. But your questions do not have to relate to any of them. That's just generally what people ask about. And but if you have any like general questions, please just throw them in the chat. Or if you have any specific questions, throw them in the chat as well. Or just take yourself off mute. I don't really have a preference. And then this will be posted afterwards once I get ready for bed. So just be patient and I'll get posted that as soon as possible. Okay. So there were a couple of questions that were asked. And I want to I'll go over them a little bit. I'll kind of try and jump through all three of them that were answered or that were asked in the chat. So I have a couple of questions also about diproducts. So I'm going to start there. So if we're looking at a acid or a base, most often we see diproducts as acids, but we do have some examples of diproducts and bases, and those are going to be 3 of your 6 strong bases. So we have calcium hydroxide, strontium hydroxide, and barium hydroxide. These are all diprotic bases because when these break apart into solution, these will cause calcium 2 plus and 2 OH minuses. So you have 2 of those OHs. Okay, so that would this is important because if you have a concentration of your initial base, of your strong base, that means that your hydroxide concentration is going to be twice the amount that you need to use for your pH. Okay, so if you start off, you have 1 molar calcium hydroxide, then that means at equilibrium, you have 2 molar hydroxide ion concentration. Okay. Where we mostly see this is diproducts in acids. Can someone tell me what our diprotic strong acid is? Anyone know what our diprotic strong acid is?
It's not sulfuric acid, is it?
I believe it is. It should be.
Yeah, H2SO4.
H2SO4. Okay, this is a diprotic acid because we have 2 of those hydrogen ions that our sulfate ion can give up in solution. Okay, so what's important to know about a diprotic acid, or just a diprotic in general, is that when this dissociates, we have a strong acid, it'll dissociate into H plus and HSO4 minus. Okay, that's the only thing that it fully dissociates to. No H2SO4 will exist. It completely dissociates into H plus and HSO4 minus. Okay, so this K here is something really big. Okay, because you have all products at the end of this. What becomes amphiprotic is H2SO4. Because it can either accept a proton or it can give up another proton. When HSO4 minus gives up another proton, this is when it causes it to be an equilibrium. So you get H plus and SO4 2 minus. Okay, is HSO4 minus a strong or weak acid here? Right, just HSO4 minus, strong or weak?
Is it weak?
It is weak, right? Equilibrium will form for a weak acid. HSO4 isn't a weak acid because it came from something strong. So its conjugate base is now a weak base that now turns into your acid that you're starting with, forming an even weaker conjugate base, okay? Your Ks will always decrease as you remove H's from your starting material. So if you have something like, I gave this example last night, H3PO4. Okay, this now has 3 ions that it can give up. So this can go into H2, H2PO4. It then can go minus, it then can go to HPO4 2 minus, and then all the way down to PO4 3 minus. And so the Ks for each of these afterwards will all form equilibriums. And this K will be, or so you have K1, this will be K2, and this will be K3. K2 will be less than K1, and K3 will be less than K2, which is less than K1. Okay, any questions on like diprotics and how you could use them? In terms of a acid-base question, you could ask something where it's like, I'm making numbers up. So if the math doesn't work, the math doesn't work. Okay, but you can have this question here where you have a 0.155 molar H2SO4 starting material, and you want to know what is the pH of the final solution. Pardon my English in the question. I'm just throwing it together. And you're given the Ka for the HSO4 minus. Right, so we just wrote out what this would, so how we would solve this is by first writing out the equations of what's happening, right? We need to know chemically what's happening. We just wrote this out. We know that H2SO4 will completely dissociate into H plus and HSO4 minus. Okay. That HSO4 minus will then form an equilibrium of H plus and SO4 2 minus. We know that Ka here is 3.35 times 10 to the negative 9. So what can we do? Can someone tell me where we would start for this type of question? And if you don't know, you can just say you don't know.
Would you turn the Ka into pKa?
You actually do not need pKa for this question, but I like your thoughts. So nope, go ahead.
Could you find X using like the ICE table and Ka?
Yes, absolutely. So we will eventually need to use our ICE table to find X because X will be our H plus concentration. But we need to take an extra step when it comes to diprotics. So I'm just going to move this down a little bit. We know that we start off with 0.155 molar of H2SO4. We know that strong bases will completely dissociate, so that all of that H2SO4 will turn into H plus and HSO4 minus. So what is our concentration of H plus right after H2SO4 completely dissociates?
Zero point one one, 0.155 molar, correct?
Yep, perfect. Right, so we have 0.155 molar. And then that also means, since there's a 1:1:1 ratio, that we have 0.155 molar here. Okay. This then turns into your equilibrium. So if we want to write our ice table, for this reaction here, what's our starting concentration for our HSO4 minus?
Starting concentration for our HSO4 minus is 0.155 molar.
Yep, perfect, right? We know that it's 0.155 molar because we just made that from the initial dissociation of our strong acid. What's the concentration of our H plus?
The same.
The same, yep. We also have this in solution already. Do we have any SO4 2 minus?
No, ma'am.
Nope. Right, so now this just turns into a regular ice table. So now you can do your changes. We don't have any SO4 2 minus, so we have to form products. If you solved for Q, Q would be equal to 0, which is less than Ka here. So we have to change to form some product, which means we're going to increase our H plus concentration. So at equilibrium, we'll have 0.155 minus X, 0.155 plus X, and X. For the most part, for most of your ice table Ka value stuff here with your changes, you're going to be able to use your assumption where your changes are going to be negligible. I would check to make sure that if you don't get the correct answer for something, or I would go back and double check if you have time that the assumption is correct. But with something of times 10 to the negative 9, that's going to be super small, where you will not have a lot of change for them, and you can use the assumption. General rule of thumb that I follow, that I was taught during my undergrad, was that if your Ka value has an exponent of times 10 to the negative 5 or greater, as in -6, -7, -8, then you can use the assumption and it will, like, 99 out of 100 times work for the assumption. Good question. So it's also going to be H plus because in our dissociation of our strong acid, we formed 0.155 molar of our H plus. So that's already in solution. That's going to contribute to our equilibrium because it's already there from the dissociation of that initial proton. Okay. So now that we have our ice table, we can throw this into Ka. So we know that we have 3.35 times 10 to the negative 9. We have X times 0.155 and 0.155. Oh, time to go to bed. So we get that 3.35 times 10 to the negative 9 is equal to X. So we know that we have 0 concentration for SO4 2 minus because from our initial dissociation of the strong acid of H2SO4, we don't form any HSO4 minus. So at the beginning, there's none of it to begin with, and we don't form it until we form some HSO4. And we don't do that until we completely dissociate our H2SO4. Okay, so once we know that X is equal to 3.35 times 10 to the negative 9, we need to know that we're looking for pH. So we said that pH is equal to the negative log of H plus. And here, even though we said that the assumption was negligible, I would still do your calculation when you're trying to solve the final pH. So you say you have 0.155 plus 3.35 times 10 to the negative 9. I don't know what that is. So I get that pH is equal to 0.81. Someone check my math. Did they also do it? Yep. So I also got a question that, okay, great. So I also got a question that the Ka did not change because we did not combine any reactions, and that is correct, right? We didn't have to combine any of our reactions, and so we can just use Ka as it is. We used the forward direction as it's given, and so we don't need to like reciprocal it, like take the inverse of it, because we're just using the forward reaction as given. Okay, so we'll use pH is 0.8. So this doesn't have a lot of effect on what pH of what the pH of the strong acid would be, right? If you plugged in the negative log of 0.155, it's going to be very close to 0.81, which is again why we can use the assumption. But this just shows you that it'll be slightly higher than I'm sorry, it'll be slightly lower in your pH than the initial deprotonation, because you are contributing a little bit extra H plus ions to your solution. Does that make sense how we would use a diprotic acid question in the terms of an ice table and everything in between? Okay. Okay, and then I think the last part of the question that was initially asked was just about using multiple Kas or Kbs to solve a problem. As in like combining a reaction or combining a couple equations to get a overall reaction. I cannot think of an example off the top of my head right now, but we can just talk about what you would do in order to solve that type of question. So if we had a reaction, just very general, where it's like A plus B, we'll say goes to H plus and C. And then we also know that we have D plus H plus goes to E. And we're given a Ka of, we'll just say 3.0. And we're given a Kb of we'll just call it that. Okay. If we're looking for the overall reaction, of A plus B plus E goes to, I guess, H, we'll just call it 2H plus C plus D. All right, if we're looking for this overall reaction, what would we need to do in order to flip or in order to manipulate your equations to get to that final overall reaction? Yep. So I have an answer for the inverse of KB and then also flip the second reaction, and both of them are perfect. So we know that we need to flip this reaction because we need to make this E goes to D plus H plus. And if we're flipping the equilibrium, right, these should all be in equilibrium. If we're flipping the equilibrium, we're flipping the equation, that means our K would be written differently. How that's written differently is if we take KB to the -1, which would be 6.5 times 10 to the -10 to the -1, and that would flip your reaction as well. So if we want to find the overall K value, we would have to combine Ka times Kb to the -1. Okay, we're adding them together, but that means you need to multiply them because when you write out the K for this overall reaction, we get H plus squared C times D all over A times B times E. And in order to get to that, you had to multiply your Ka times your Kb. Okay, so we could say that this was 3.0 times 10 to the -5 times 6.5 times 10 to the -10 to -1. Right, and just that 6.5 is to the -1, not the 3.0. And I got K is equal to 4.6 times 10 to the 5th. Okay, is there any questions how we manipulate K in this scenario? Does that help clear up our questions on combining equations? Are there any other questions on what we just covered? I know that's not like a practice exam or question or an homework question, but good questions all around. Does anyone else have any specific questions? I think someone did ask for the 6 strong acid or 6 strong bases earlier. Can someone tell me what they are? I gave you 3. I gave you calcium hydroxide earlier, strontium hydroxide, and barium hydroxide. What else is there? RBOH is not one of them.
Lithium hydroxide, sodium hydroxide, and potassium hydroxide. Okay, okay. Thank you.
Yep, perfect. So on the periodic table, if you look at this, it goes lithium, sodium, potassium, calcium, and I always forget if it's either strontium or barium first. I won't tell you the wrong information. It's strontium, and then it's strontium and barium. So this is what it looks like on the periodic table. So if you ever need to follow what your 6 strong acids are, just going to start in the top and go down and over, right? You know that there's 6, so you have to go 1, 2, 3 over for 1, 2, 3. Okay, that's just visually how you can use the periodic table to memorize your 6 strong bases.
Quick
Yep.
question.
Go ahead.
Is calcium the stronger strong acid compared to potassium? Or that trend doesn't really work like the same way for the acidic?
So if we are looking at like acidity, right? We increase acidity going across the periodic table.
Yeah.
So we will decrease basicity. Basicity going across the same rate because it's going to be equal and opposite.
Okay, gotcha. Thanks.
So I think generally your potassium should be stronger than your calcium.
And then the rest you know based off of it going down.
Yes. Yep.
Okay, thank you.
Let's just make sure that that trend also exists that way. We'll ask the Google machine. Google machine is not. Okay, yes. KOH is the stronger base. Yep. Okay, thank you, Google. Yep, so that trend works for that one still. It should have, I just don't want to tell y'all the wrong thing. Okay, perfect. So then in the chat, we also have a question about Lewis acids and bases. So when we talk about Lewis acids and bases, your Lewis acid is going to be your electron pair acceptor, and your Lewis base is going to be your electron pair donor. Okay. Questions on what that means just in terms of a definition? Alrighty. So how we see this in action? I think it's easiest to see what a Lewis base looks like and how that acts. A lot of the times you will use the weak base of NH3. Okay. If you write out the Lewis structure for NH3, you will see this lone pair. This lone pair on top of the nitrogen is what's donated during this acid-base exchange. Okay. What is the, if we have NH3, what is the conjugate acid of NH3?
Would it be NH4 minus?
Close.
It's the H that was lost. Wait, is that right? No.
So I like NH4. Is the hydrogen going to be positive or negative? It'll be positive. So this is going to be NH4 plus. And this is ammonia. And this is ammonium. In case you need to see either one of those. So what happened, right? In this electron pair situation, we're giving up that electron pair. So instead of having the lone pair now, that's taken away, right? Our electrons are negatively charged. So we no longer have those negative charges, creating a positive charge. But now we have an extra H on our nitrogen. And that H will have a positive charge associated with it. So when we subtract, when we donate that lone pair, we're now -2 on that nitrogen, but we gain a +1 from that hydrogen. So we end up with NH4 plus. Okay, so the electron pair is being donated and being replaced with a hydrogen instead. For the acid, it's doing the exact opposite. It is giving up that proton and allowing the electrons to come in, right? So they're doing an exchange of an electron for a proton, right? Going back and forth. Your conjugate acid will always be one additional hydrogen more than your base, causing a positive charge to form. And your conjugate base of your acid will always be one less hydrogen than the acid, which is going to cause a negative charge to form. And that has to do with the exchange of protons and electrons between your acid and conjugate base, or base and conjugate acid. Most of the time, a cation will be the acceptor, where it's accepting electrons to negate its positive charge, and like a non-metal ligand or some sort of other complex will be your donor.
In the notes, when he talks about Lewis acids, he starts going into like the sp3 and like the orbitals and all that stuff. Do we really need to know a lot of that for this test?
I would say probably not. The idea behind those sp3 orbitals and everything that he was talking about is the fact of what's able to accept a proton and what's able to donate an electron. So as long as you can know or have a way to figure out what has an electron pair to donate and what might be more of a positive charge, you shouldn't have to worry about those sp3 orbitals and that in-depth of a knowledge for defining what a Lewis acid and Lewis base is for this exam.
Okay, thank you.
And yes, so there's a very good question in the chat. It says, can ammonium be considered an acid or just the conjugate acid? So anything can be classified as an acid or a base, and anything can be classified as a conjugate acid or a conjugate base. In the context of NH3 and water forming an equilibrium, which one is your base here? This will be your base, which means H2O is your acid. Making NH4 plus, right? One additional hydrogen is going to be your conjugate acid. And OH minus is going to be your conjugate base. And this connects this to this and this to this. However, we can also put this in the context of NH4 plus in water. And this now creates NH3 and H3O4 or H3O plus. Now in this case, NH4 plus is your acid, water is your base, NH3 is your conjugate base, and H3O plus is your conjugate acid. So it just depends on the context that you're speaking in of whether it's considered a conjugate acid or just a straight up acid. Any other questions? Any questions on the practice exam, on the homework? Did everyone see my solutions? Did that help? Anything else you want to see from me right now?
I did
Yep.
have one question on
go
the
ahead. Sorry, go ahead.
on the practice exam on number 14. I understand how you got everything, but I'm just confused on where you got where the x is squared.
Yes. So when we're looking at methylamine here for this question, this is given at the top of your exam in case you missed that. But this is methylamine right here. So this is NH2 and then CH3. So if we were to put this in the context of like in solution in water and form an ice table, we would get water here. And we would form, we have a nitrogen, and this nitrogen is going to be indicative of the base. We also are given at the top the Kb for this methylamine, and that should be a indicator that it's talking about a base. They're most likely going to give you the Ka or Kb, depending on if it's most likely going to be an acid or most likely going to be a base. And so here it's acting as the Kb or the dissociation of the base. So that's why it's going to act as a base here. So in that context, we're going to form NH3 plus CH3 and OH minus. If we were to write an ice table for this, we have some initial concentration. I'm just going to call this initial. We don't have a concentration for our 2 here. This would be minus X. This would be plus X, and this would be plus X. So at equilibrium, we would have initial minus X, X, and X. Based off of the information given in this question, we know that pH is a solution of 8.7. So we can say that pH is equal to the negative log of 8.7. sorry. No, we can't. We know pH is equal to the negative log of H plus. So to find the H plus ion concentration, we would say that 8.7 is equal to the negative log of H plus. To get rid of this, we have to divide by 1 and then take the base 10. So this becomes 10 to the negative 8.7 is equal to H plus. And I don't remember what that is, but I'll do it real quick. And this is 1.9, 2.0 times 10 to the negative 9. But that is pH, right? You can then solve for POH. Sorry, I did this backwards. We have pH. We know that this is equal to 14 minus POH. Oh, dear God. It's getting late. I can feel my brain shutting off. It says 14 is equal to pH plus POH. We have pH. We can say that 14 minus 8.7 is equal to the POH. So the POH is 5.3. You then do that same thing that we just did for pH. So you say 10 to the negative 5.3 is equal to P is equal to the concentration of OH minus. And this is 5.01 times 10 to the negative 6. This is our concentration of OH. This here is X. What else is X in our ice table is that other product. So when we write Ka, or when we write Kb for this, oops, we know that this is going to be NH3 plus, CH3, OH minus, and then that methylamine. So since these are both X's, here, and that matches the same concentration as our OH minus, we can just call that squared because it'll just be the same thing times the other one. Does that make sense of why it's squared?
Yes, it does now.
Okay.
I thought it was coming from the equation or like the reaction, because then you put it 2x or like that number over the initial. So
yeah,
I got it now.
Yep.
Perfect. Thank you.
Sorry, I did it, I guess, like a shortcut in terms of writing out my stuff.
No, you're all good.
Yeah. Okay. And then I had one more question in the chat just about what we were talking about right before that. So when it comes to your conjugate acids and bases, you can have, I guess, 4 necessarily different scenarios in terms of your acid, or in terms of your initial acid or base, and then its conjugate acid or base. You can have a strong acid and a weak base. You can have a strong base and a weak acid. You can have a weak acid and a weak base. And you can have a weak base and a weak acid. You can never form a strong conjugate. Okay, you can form something that is stronger than your initial, right? So here, we'll call this here. In this example here, your weak base could be stronger than your weak acid, but that does not make your weak base a strong base. That just means that it's a stronger weak thing. Okay, does that make sense in terms of strengths of conjugates. Cool. I think that's important to know. You can only form weak conjugates. All right, anything else you want to see or have questions on? Do we feel ready? The practice exam go okay? Okay. If there's no further questions, I won't take up any more of your time. I'll hang out for a couple more minutes, but I guess I'll just give my pre-exam stuff right now. I hope this is the last you have to look at chemistry for the night. Make sure you get a good night's sleep, and you allow your brain to rest and recover and retain all of the information that you have studied very hard for. Tomorrow it will be another long exam. I think a lot of people realized how long these calculations take after exam 3. So take your time, but make sure that you are moving efficiently. If you don't know the answer right away, or you don't know exactly how to get to your answer right away, skip it and come back. It's best to give your brain a little bit of time to maybe think about the question as you're working on other things, and then you can come back to it once you've given it a little break. Use the test to your advantage. See if you can have a question that helps you out here or there, solving for something else. During your true false questions, always make sure that you are asking yourself, is this always true? Can I prove this incorrect, right? If you can come up with a scenario where it is incorrect, call it false, and trust your instinct. If you think it's false, it's probably false. Think it's true, it's probably true. And then just make sure you answer every question. Multiple choice, so at some point you do have a chance of guessing correctly, if worse comes to worse. I will be there during the exam again, so if you have any questions, please let me know. And if you have any questions in the meantime, feel free to email me. I will post this as soon as I get the link back from Zoom. And if you need to reference this again, and I guess good luck. I'll hang out for a couple more minutes, but if there's no other questions, I'll say good night and thanks for coming.
I have a question about one of the true or false questions.
Yeah, absolutely.
For P8 on the practice exam, it says if 9% of an acid ionized in water, that the acid be considered weak, and that's false.
Okay.
Whenever it says that it's only 9% ionized, so why would we consider that a strong acid if not 100% of it ionized?
I believe that most of your acids don't even go that far.
Okay, yeah.
So if we can just take, right, we'll just take a look at NH4 plus here. Right, if we just made up something, we have NH4 plus H2O. This would become NH3 and H3O plus, right, which is hydrogen. Okay, if we said this was 1 molar for your ice table,
Mhm.
so that started off that way. Right, we have 0, 0, minus X, plus X, plus X, 1 minus X, X, and X. We
Mhm.
solve for X, we're trying to find our percent ionization. Right, we get 5.6 times 10 to the negative 10 is X squared over 1. So X would be equal to
Itty bitty number.
itty bitty number, I believe. Yeah. 0.01, 2, 3, 6, 6. Right, so this is how much is X. If we're
Yep.
talking about percent ionization, this is
Yeah, that's
percent of 0.0000236664 over 1, right? Because that's our initial
yeah.
times 100. So if we do times 100 of this is only 0.0024% is ionized, right? So
Yeah.
the weak acids, I think, don't even get close to 1. So we say it's 100% ionized, but really, and that's why, right, I say you have 6 strong acids and 6 strong bases because that's
Yeah.
all you know for this exam. But there are strong acids that we don't consider the 6 strong acids because they do get up to that 5%, 9%, 12%
Okay.
ionization.
Okay. Yeah.
But they're just, that would be too many things to know for the scope. So I think the threshold might be like 1% is when it becomes a strong acid. But yeah, if you kind of look at some of your other Ka values, if you pick a higher one, like right, HF or
Yeah.
right, I think that's the highest one on this list. If you do the same thing that we just did, you can see how much that percent ionizes. Honestly, we can just do that real quick because that's just the square root of the Ka.
Yeah. That's just a square root. -4. Is that, yeah, 3%?
I typed in the wrong number.
Oh, wait. No.
Yeah, that's 2.7%.
Yeah.
Right. So yeah, so someone just said in the chat the cutoff is less than 5%. And so I think that's like the correct one. I couldn't remember just now, but I think the cutoff for the weak acid is 5%. Right. So this one is 2.7 and therefore would fall less than 5%, which is considered weak.
It's kind of wild. For some reason, I thought I had recalled in lecture that you like it 100% ionizes, so it's strong. And then I guess that like just stuck with me.
Yep.
I
And
understand.
yeah, that's what everyone tells you too, right? Your 6 strong acids that you are required to know will 100% ionize, meaning that it does not form equilibrium, right?
Okay. Yeah.
You can never have a solution of that HCl, Br, HClO4. You can never have a solution of that. It'll always be in its H plus and
Ionized ion form.
Yep, in its ionized form. You can still have strong acids, but they then form an equilibrium. So they are not 100% ionized, but a lot of H plus exists in those solutions. And that's what causes them to be considered a stronger acid than other ones, but they don't, but some of that initial acid still exists. And that's why it's not a strong acid as in it 100% ionizes.
Yeah. Okay.
It's good to think that your 6 strong acids will 100% ionize because that is true.
Yeah. But the actual like concentration, percent concentration is, yeah.
Yep. Good question.
Is a good way to remember the pKa and pKb, as in like just remembering like parts. Wait. Sorry, that was a thought that I had like many hours ago, and I've kind of like lost it.
I guess what are you trying to memorize for pKa and
Um,
pK?
here's a question. To go from pKa to just like Ka, you just raise 10 to the power of whatever the what
Yes.
is that?
Yep.
Yeah.
Yep.
Okay.
Because you are always going to be using that log function whenever you
Yeah.
have the p.
Yeah.
And so in order to negate, right, like
Yeah.
undo
I
that
do.
that log is to
Put to the power of
base
10.
10 it, which is the power of 10. Yep.
10 to the power of. Yeah. I've kind of like just have memorized that as like parts Ka or part Kb.
Mhm.
Just because like pH and POH, I just remembered as like parts hydrogen, parts hydroxide. I think
Mhm.
that's right.
I think
Hydroxide.
I think that should be correct as well.
Yeah. It just like makes sense.
Mhm. And then someone just asked if bases will, or strong bases will also completely ionize, and that is true as well. So if you have like lithium hydroxide, that will only exist as lithium and hydroxide ions. Um, calcium hydroxide will only exist as calcium and hydroxide ions. And that's why we talk about at the very beginning, your calcium hydroxide concentration might start off as 1 molar, but your hydroxide concentration is 2 molar because all of that initial concentration of your calcium hydroxide turns into ions. And we have a 1 to 2 molar ratio between the calcium and the hydroxide, therefore doubling the concentration of your hydroxide ions in solution.
Whenever you're solving for x, will x always equal the H plus? Like, will it ever equal OH minus?
It depends on if you're talking about Ka or Kb. So if we're given a Ka, we're given a Ka, this is the acid dissociation, which means we have our acid that's dissociating into H plus and its conjugate base A minus. For Kb, we have the base dissociation, which means that we have our B minus and water. Water as the acid is going to donate a proton, forming the conjugate base HB, or I'm sorry, the conjugate acid HB and OH minus. So if we're solving for X in terms of Kb, X would end up here and here. And so X here would be equal to your hydroxide ions concentration. So if you want to find what pH is from this scenario, you have to find the POH. And then say that 14 is equal to pH plus POH. And then solve for pH that way. And then Adrian, I see your last question were are weak bases defined the same way as weak acids? In what context?
The 5% rule.
Yes. Yep.
Okay.
Yep. So if you have a weak base, then that will be less than 5% ionization.
All right. Thank you.
Yep. Alrighty, I think it is 9:30, so I will officially sign off. Have a great night and good luck, and I'll see you tomorrow.
Thank you, Allison.
Thank you. Good night, y'all.
Excuse me, I have one last question. Could you explain number 8, please, again?
On the homework or practice exam?
Practice exam.
Yep, so the cutoff for a strong acid, like a strong or weak acid, is going to be percent ionization is less than 5%. So anything above 5% would be considered a strong acid. But for the context of your exam, your 6 strong acids and your 6 strong bases will 100% ionize. And those are the only strong acids you need to know. But if you're given a true false question and you say a weak base has a percent ionization of 2.5%, that would be true because it's less than 5%. And that falls under the category of being considered a weak acid or base. Does that help?
Perfect. Yes, thank you so much. I know
You're
it's
so
past 9:30.
No, it's okay. Alrighty, I am officially signing off. Good night, y'all.